All right. Good afternoon, good morning, good evening, class, whatever time it is. This is our day 14 lecture video covering our last section of chapter 5, where we're going to be looking at section 5.3 of our textbook. So I'm going to go ahead and share my screen here as we're going over the schedule. So we are covering in day 14, section 5.3 of the textbook. All right. So we're going to be focusing on the end of chapter 5 here. We're only covering one section in this video, so it might end up being a little bit shorter, but this section is super, super important. So I wanted to have this dedicated lecture to this single section here as we cap off chapter 5. All right. Also, you'll see that we do have test 2 is coming up. I'll also be posting an announcement in Canvas with more information on test 2. That's going to go the same way that test 1 happened. So there will be review questions posted you can go and look at, as well as you have all the homeworks you can go back and look at for practice. And during that time, while you're studying, if you do have any questions, by all means, please do email me. Come by office hours, let me know what your questions may be, and I'm happy to try to help in order for you to better prepare for test 2. All right. So that is coming up. Be mindful of that. We also have some homeworks. Homeworks 12 through 16 are going to be due, um, let's see, on day 15. So those are coming up. Those homeworks are related to this chapter 5 material, some of the chapter 4 material. So while those homeworks are not due yet, those can also be good practice for the test. If you understand those homework questions, that's going to help prepare you for this chapter 5 and later chapter 4 stuff that can appear on test 2. Okay? With that being said, let's go ahead and jump into test 2. So I'm turning off the screen share as we go to the board behind me. And at long last, we are ready to talk about the normal distribution again. Recall back on test 1, we talked about this normal distribution where if we're considering a population of data on some event, whether if we're talking about IQs or we're talking about heights, where your average height is, clustered here in the middle. We have the Greek letter mu for a population average. You have some people who are taller, and there's a few people who are like the tallest of the population, and there's a few people who are the shortest of the population. But most people, we have this higher frequency clustered around the average. All right. So this kind of shape for a distribution is super common for a lot of different things in the world, whether we're talking about height, IQ, test scores, SAT scores, BMI, all sorts of things where we see this kind of pattern appear when we're looking at an entire population of some data. All right. So, with this in mind now, based on what we already know in chapter 5, if I think of this as I take a random person from a population that looks like this, right? Let my random variable x be a randomly selected person from a population. Now, of course, when we're talking about um, the normal distribution, it's not always about people. This could also be about cars. This could be about the battery lifespan for a car battery. How long is a car battery going to last? Most of the time, most car batteries are going to be somewhere around the average for whatever the average lifespan is. A few batteries might last absurdly long, and a few batteries, just bad luck, might die very quickly. All right, so it's not just about people, but it's just a random object or a random entity which is picked out of a population of data where the population takes on this kind of shape. All right. Based on what we know in chapter 5, in order to calculate probability here, we're asking about finding the area under the curve. So if I have, for example, some A and B here, and I want to know, well, what is the probability that this random X is between A and B, so I'd write this as the probability of X being between A and B. What we're really asking here is what is the area of this shaded region? What percent of the entire population is represented by this shaded region, right? Um, the cat is playing with the box. Let me put her out of the room real quick. What are these? Gator. All right, sorry about that. So we're looking for the area of this shape, this shaded region, which is underneath the curve, okay? Now, the trickiness is, okay, well, what is the function that represents this normal hill shape, this bell curve shape? What is the function for this so that we can find the height and therefore try to find the area of the shape? Well, unfortunately, because it's got all this curved surface to it, the height is changing for all these different x's between A and B. And so to really find this area, we would have to take the integral of this function from A to B. We would need calculus. Now, don't worry about that. This isn't a calculus class. Instead, we have a handy table from the textbook where those integrals have been calculated for us. All right, so we're not going to have to do that. We'll look at that table in a moment so we can understand how to read it. But I first, just for the sake of explaining what's happening here, let me just go ahead and write up what this function is that represents this bell curve hill shape. All right. So this function, and you don't have to memorize this, so don't worry about it. I'm just showing it here for sake of clarity and explanation. F of x equals, so this is the function for this curve, 1 divided by the standard deviation times the square root of 2 pi times the number e raised to the negative 1/2 power times, and now here's something interesting that we should recognize, x minus mu, that's the average, divided by the standard deviation, and then this is squared at the very end, all inside of the exponent, all right? This, of course, super messy function, kind of messy, a lot of work to try to integrate this. We're not going to do the calculus with this, all right? The point here is that this is the function which represents this curve, and we can use calculus to find the area of these different shaded regions. And the tables we'll look at in a moment, are the integrals which have been calculated for us, okay? Where they're taking the integrals of this. So that's what those tables are when we look at them later, all right? But what I do want to highlight here is take a look at what appears here in the exponent. This is x minus the average divided by the standard deviation. Well, what is that? Think back to test 1. That's our z-score. Z equals x minus the average divided by the standard deviation. Okay, well, that's interesting. What was the z-score all about? Recall, z was the number of standard deviations away from the middle. All right? So if I erase some of this picture at the moment, just, trying to back up, what do we recall from test 1? As this stuff will come back to get us here at the end of chapter 5. I'm erasing part of this. Okay. So back up. What did we know from test 1? If I have some number over here to the right, which is 1 standard deviation to the right, so I'm adding 1 standard deviation to the average, right? So I'm using lowercase sigma, that's our standard deviation symbol. This is the average plus 1 standard deviation. So this line would correspond with when z is 1. That is 1 standard deviation to the right. And we had an empirical rule that we used back then on test 1, where if you look plus and minus 1 standard deviation to the left and right, this entire region is approximately 68%. That's what we had from the empirical rule. It was an approximation method for finding the percentage of the population represented here between plus and minus 1 standard deviation. This is when z is 1, right? And so this formula here, no coincidence, is popping up again as we're looking at finding probability with now any possible z value, right? If z is not 1, 2, or 3, we can now use the table to determine, well, what is the probability for those regions, all right? So we're going to go to the textbook here to see how this works. But we're also going to see how does this align with what we already know for the empirical rule, okay? So let me erase some of this. So we have this big nasty function, f of x. Don't worry about it. We're never going to see it again. But what we are now concerned with is, well, what does it mean when z is 1? When z is 1, this means I'm looking at some number which is 1 standard deviation above the average. All right? So we go to the table. I'm going to share my screen here. And this is in section 5.3 of the textbook on page 240. And here they're just giving us the formula for that function again. We don't need to memorize it. Don't worry about it. The big takeaway here, though, is that because z does appear in the formula, we can simplify the formula where instead of thinking of it as a function of x, we can think of it as a function of z. And you can see here that when we replace x minus the average divided by the standard deviation, we're going to replace it with z, and now my formula is a little less complicated, all right? A little easier to look at, a little easier to work with, okay? So when we change x to z, then our graph looks like this, where a z of 0 means I am 0 standard deviations away from the average. In other words, when z is 0, that's where the average is, because it is 0 standard deviations away. If I go 1 standard deviation above, that's 1 standard deviation plus the average, so on and so forth. And so I can break up this graph into pieces where I go a z number to the left and right. All right, so that's what this picture is. Now they make a note here that in order to determine probability, we are using calculus and we're taking the integral. All right, so that's where these probabilities are coming from. But lucky for us, this table, now this is a shortened version of the table. This same table is found in Appendix B, which you're going to want to reference for the homework. So if you go in the table of contents for the textbook, scroll down to the Appendix B tables, then what we're looking at here is the normal curve area table. All right, so it's the same table. This table is bigger because it has more possible z values. All right, so you're going to want to use this when it comes to the homework. But for what we're doing in the textbook right now, we can use this smaller version that's in section 5.3. All right. So what is this table doing? Well, the table has calculated these integrals for us, where whatever z value you're thinking of, here's the shaded region. It is telling you what is the area of that region from the middle, so that's from 0z, or in other words, that's from the average up to that z value. Now, it's a positive z value, but that's okay. We can still use that. This is from the average up to the z value. It's telling us what is the area for that region. In other words, what is the probability for that region? What is the probability of picking a random object from the population, which will be in that range from 0 to z? Okay? Now the way to read this table, going down the left side, these are the different z values out to the first decimal point. So 0, 0.1, 0.1, 0.2, 0.3, so on and so forth. But then we have these other columns, which is asking, well, what is the z value in the second decimal place? All right. So just, a quick example. If z were, and I'm just making this up, let's say 0.14. Okay. Then what do we get from the table? The table is telling us then that the probability of some random x, or in this case, we're looking at a z, some z value being between 0 and 0.14, right? That's the region we're looking at. That's from the middle, when z is 0, up to 0.14. What is the area for that region? What is the probability of that region? Well, 0.14, so I go down. Okay, I'm looking at the 0.1 row. Now I'm going to go to the right until I hit the column, which has a 0.04 in the second decimal position. So I go to the right. This is 0.10, 0.11, 0.12, 0.13, 0.14. So here's my answer. We have 0.0557. And so the table has calculated the integral for me, so we don't have to do any calculus. They've done all of these integrals for all these different z values, so that we don't have to calculate any of them. All right. And so this is telling us then, well, what percentage of a population is between 0 and a z of 0.14? A little more than 5%. So that's 0.0557, or in other words, 5.57%. We could write it as a percentage. That would be 5.57% after we move the decimal point. Okay? So that's how we read this table. Now, what I really want to highlight is come back to what we just had on the board here. We said the empirical rule, plus or minus one standard deviation, is supposed to be 68%. Does that match up with this table? How do we find out? Well, if we come back to the whiteboard for a moment, the table that we were just looking at, it can tell me, well, what percentage is between the average, which is when z is 0, up to z equals 1, right? It can tell me this right half. Well, recall the normal distribution is symmetric. The average down the middle is completely splitting this in half. So whatever I find from the table here, when z is equal to, we'll just go ahead and call it 1.0, that's telling me the percentage for this right half. Well, if I double it, that will tell me the percentage of this left half. All right, so we're going to see if we go with this more accurate method with the table, which is based off of calculus and integration, this is going to match up with the 68% approximate answer that we used back on test 1. So we go back to the table. I'm going to share my screen again. And we're looking for the z value at 1.0. Okay, here's 1.0, and it has a 0 in the second decimal point. So we're looking at this spot here, 0.3413. All right, 0.3413. We go back to the whiteboard. And so that means this right half is 0.3413. Okay. Well, if I double it, because the other half is just the same thing, but on the left side, so then double it, and we find out the probability that z is in between 1 standard deviation or -1 standard deviation. So that's -1 standard deviation to the left, 1 standard deviation to the right, is, if I double this for this region, I'm getting 0.6826, right? Which, all right. So the empirical rule with this 68%, that's pretty darn close to 0.6826, all right? Now this 0.6826 is more accurate. This is a more accurate answer because this is based off of the calculus. This is based off of integration to find a more exact answer for the area of this region, okay? So 68%, this was a pretty good approximation to get us started back in chapter 2 when we were working through the test 1 material. But now, with this table, we can find more exact answers for these different regions. Okay? So this does match up with the empirical rule, and we're using the table to figure out what are these regions from the middle up to some z value. All right? Now, the rest of this video, I just want to work through some examples so we can get used to this, as it's kind of a little bit weird the first time we see this. Okay? So I'm going to erase what I have here so that I'll be able to do the same picture again. So let me erase this. And then we'll go through the examples in the textbook here. All right. So we've got that z table, which we're going to use here to our advantage. And we can also ask questions about different regions. For example, what is the probability that I have a z value which is greater than 1.64? Okay, well, draw the picture. What are we talking about here? All right, well, a z of 0, that's where the average is. That's here in the middle. Z is 0 here in the middle. A z of 1.64, that's over here to the right. Z of 1.64. And I want to know the probability of having a z value which is farther away. It's more than 1.64 standard deviations. In other words, I'm looking at this tail region. All right, that's what I'm trying to find, the shaded region here. Well, how do we do this? Well, we can use similar tricks to what we did with the empirical rule back for test 1. Recall, because the average is splitting this in half, this means the entire right side is 50%, right? Because it's split in half, half of the graph is to the right, half of the graph is to the left. Well, if this entire right side is 50%, and then the table can tell me this region, right? The table, if I look at when z is 1.64, the table can tell me, well, what percentage is between the average up to this z of 1.64. So to find what I'm actually looking for here, I can do some subtraction. The entire right side is 0.5. Okay. But I want to subtract the blue region. I don't want to count the blue region because I'm looking for what's this piece to the right of this z value. So I'm going to subtract what we get from the table when z is 1.64. All right, so that's what we're going to do here. So, all right, I'll share my screen, and we will go to the table. Sharing my screen. And we're looking for where the z is 1.64. Okay, so I scroll down. Oh, this table actually doesn't go far enough. So I'm going to go to the appendix. All right, so table of contents. Scroll down. We're going to go to Appendix B, and we're using the normal curves areas. It's normal curves areas because, well, this is the normal distribution. All right. Now, this table, it has z values going as big as like 3.09, so pretty big z's. That's pretty far away from the middle. But we're interested in 1.64. Okay, so here's 1.6. And now I need to count over to the right until I find the column which has a 4 in the second decimal place. All right, so we can see it's up here, but I just want to count over. So 0.60, 0.61, 0.62, 0.63, 0.64, we find an answer here of 0.4495. All right, so all we do now is copy this from the table. This is 0.4495. All right, that's all we need from the table. I'll turn off the screen share. And so now we're ready to get our final answer. The probability of a z-value being past 1.64 can be calculated as 0.5 minus 0.4495. Now I'm going to put that into a calculator. And we will get here 0.5 minus 0.4495 to get an answer of 0.0505. Or in other words, this means 5.05% of the population would have a z-score which is past 1.64. All right. And so whenever we're trying to determine probability for any x value, what we really have to do is change that x into a z value, and we can find our answer. Okay, but how do we find z if we don't already know z? We already knew z for this question. That's where our z-score formula comes from. So x, this is some sample point that we're trying to examine, that we're trying to study in some kind of statistical application. Mu is the average. This is the mean. Sigma, this is our standard deviation, right? We've seen this back from test 1. Z, we're going to use our z-score formula. X minus the average divided by the standard deviation. With this formula, then I can find the z value, which is associated with any possible x, so long as I know the average of standard deviation. And then I proceed to use the z-table to actually find the probabilities for these different regions. And then we're on our way. We're able to solve these questions. All right. That's the general strategy for any question here in 5.3. All right. So what else do we have in this textbook section? Let me go back to 5.3. The screen is zoomed in here. Let me zoom back out so I can see it better. All right, in section 5.3, yeah, we're looking at these different examples. All right, yeah. Calculating z with this formula, x minus the average divided by the standard deviation. So we're ready for this last example, and this example is also the exercise for our participation question today. All right, so I'm going to go ahead and move over to our participation question, and then we can talk through this step by step. So on your computer, phone, whatever you're using, go ahead and pull up participation day 13, all right? And I'm going to share my screen as we're reading through this exercise to kind of get a hold of what's happening here. Okay? And I'm going to write some notes here on the board so that we can answer the question. So let me erase what we have here. I'm going to keep the formula for z up because we're going to use that in a moment. All right? And then I'm just going to fill in information based off of what they tell us. Okay? So, reading the question, assume that the length of time, x, that's our random variable, because we're talking about time here, that is a continuous interval, right? We can have seconds, milliseconds. If you have an accurate enough kind of stopwatch, then you can measure time down to many different decimal points. All right? So this is a continuous random variable. So this is the length of time between charges of a cellular phone, and this is normally distributed with a mean of 10 hours and a standard deviation of 1.5 hours. So this is the amount of time between charges. How long does the phone last before it dies, or before you start charging it again? Okay? Now this says on average, it's lasting 10 hours before you charge it again. So that's our population average. We're given that information. The average is 10 hours, so I'm writing that on the board. Standard deviation is 1.5 hours, so I'll write that down. Okay, 1.5 hours. Now, we're asking the question here, because this is normally distributed, it's got like this bell curve kind of shape. Find the probability that the phone will last between 8 and 12 hours. It'll last somewhere between 8 and 12 hours. So we're trying to find the probability that X is between 8 and 12. All right. So I've written everything on the board here. So I'm going to turn off the screen share and then we're going to do the rest on the board. Okay. All right. So this is the question. We want to answer this. But like we just said a moment ago, when we're trying to find probability about our random variable X, we want to rewrite this in terms of Z in order to use the Z table. So what is this really asking here? Well, we know the average is here in the middle. The average is 10. And then we have these boundaries where my upper bound, this is for an X value, which is 12, right? Since X is the number of hours between charges. And then I have a lower bound of 8. So for an X value, which is 8. And I want to know, well, what's the probability of this region? Okay. Well, we want to rewrite this in terms of Z in order to use the Z table. So I'm going to use our Z formula. When X is 12, what is Z? Z equals 12 minus the average divided by the standard deviation. And so we go to a calculator. We find that Z, 12 minus 10, divided by 1.5 is this fraction, but it's a decimal with a 3 repeating. Now, we have to be very careful here. Our Z table only tells us how to find a Z out to 2 decimal points, right? For the Z table, I have the first decimal place and the second decimal place. It doesn't help me find Z's with more decimal points than that. So, in order to use the Z table, we always have to round our Z to 2 decimal points in order to use the Z table. Round 2 decimal points to use the Z table. Okay? We always have to do that. So I'll round this to 1.33. Okay? Now when X is 8, Z equals 8 minus 10 divided by 1.5. And no surprise here because 8, that's the same distance below 10 as 12 is above 10. They're both 2 away from the middle. So we're going to get the same Z value, but in the negative direction. All right, so for X equals 12, the Z is 1.33. And for X equals 8, the Z is negative 1.33. And so I can rewrite this question. Finding the probability that X is between 8 and 12 is the same thing as asking, what's the probability that Z is in between negative 1.33 and 1.33? Okay? So now we have this question rewritten. But what do we do? How do we actually find this? All right? Lucky us, notice some tricks here. Again, the average is splitting this in half, right? And luckily, I'm looking at 1.33 standard deviations to the right and 1.33 standard deviations to the left. So if I just find this one region and double it, that'll give me the entire region we're looking for. So I'll write that. This equals 2 times the probability that Z is in between the middle and 1.33. Well, now that's easier. That's just going to the table. Look where Z is 1.33, and that will tell me this region from the middle up to where z is 1.33. If I double it, then that gives me the entire area, the entire region that we're looking for. Okay, so we go to the table. And I'll share my screen here one last time. Sharing my screen. And we're going to the table in the appendix. Normal curves area. Okay, we need to find the area with z is 1.33. This is why we have to round z to 2 decimal points. 1.3 is here. 0.30, 0.31, 32, 33. Okay, here we go. 1.33. At that spot, we see this number, the area, is 0.4082. So my final answer is going to be 2 times 0.4082. All right, so we come back to the whiteboard one last time. I'll turn off the screen share. 0.4082. We're going to double that to get our final answer. 0.4082 times 2 to find our final answer. Well, the probability that it's in between 8 and 12 hours is 0.8164. Or if I rewrite it as a percentage, this means there is an 81.64% chance that this phone will last somewhere between 8 to 12 hours, right? Now that's a pretty large region or range of hours. Is it going to last 8 hours? Is it going to last 12 hours? Somewhere in between. Whatever the case is, there's an 81% chance the phone will be in that region. All right, or it'll die in that region, or it'll have to be charged in that region. All right, and so that will give us our final answer for today's participation question. All right, so you can go ahead and write that down, submit it. That will give you the answer for participation day 14. All right, so that will conclude our Chapter 5 material and Section 5.3 for our discussion of the normal distribution. After test 2, as we continue to chapter 6, we're going to do some more kind of stuff with normal distributions. We're not done with this guy. There's a lot of different applications with this sort of distribution, all right? But this kind of gets us started in this world with chapter 5 with how do we approach probability for any z value, right? Now we can do this for any z, rounded to 2 decimal points, whereas before we could only handle z values which are exactly 1, 2, or 3. All right, so now we have a little more power than we did before. So that will wrap up today. Test 2 is coming up. So if you have any questions, concerns, by all means, please do reach out to me. Let me know. I'm happy to help. Otherwise, that will be it for this lecture video. I wish you the best of luck, and I will see you in the next video. All right. Have a good day or have a good night.